my name is Lucas, and this is my final hardware project 3.7 gray code. This project takes input from this gray code dial or 4 dip switches and displays their hexadecimal output on the 7-segment display. This circuit uses combinational logic, which just means a series of logic gates like AND, OR, and NOT chips. To come up with the proper circuit for this, we use Boolean algebra, or more specifically K-maps or Carnot maps. K-maps are a visual way to demonstrate Boolean algebra and simplify logic expressions. Although expressions can be simplified using Boolean algebra laws, it can get complicated quickly, and there's really no way to tell if your expression is actually as simplified as it can be. In K-maps, it's all visual, so you can actually see if there's a simpler way to show this expression. But how do these things actually work? This is an example of a pretty simple K-map. There's 4 variables, which is why it's a 4x4 square. K-maps are basically big truth tables. If all the variables that correspond to this square here are true, then the circuit will output a positive. And if all the variables here are true, that correspond to this square or true, it will output a 0 or a negative. In this map, the circles are 1s and the blank squares are 0s. In order to find an expression that describes this scenario, we must group all the 1s together. The easiest way to do this is to start with the biggest possible group first and then work your way down to the individual squares. In this example, we start with the biggest group, and that's this big 2x4 group. Then either the smaller 4x1 group or this 2x2 group. As you can see, the K-map groups are not confined to the actual grid, and they can cross over. For this project, custom K-maps were created for each pin on the 7-segment display. So there's 7 custom K-maps. Then I found the operations that were the same on different pins of the 7-segment display because it's really all one big circuit. So I found operations that were repeated on different pins and simplified them to just 1. For example, A prime is always A prime. So instead of doing the operation A prime, which is called like 30 times during the entire circuit, you can just do it once and then spread out that output and connect it to each pin that requires A prime. This reduced the NOT operations from 38 to 4 and the number of NOT gates required from 8 to 1. And the exact same thing was done for all AND and OR operations, but on a much smaller scale. In the end, I was able to get the number of chips down to just 13, 6 OR, 6 AND, and 1 NOT chip. This was useful because gates cost money, and especially for big circuits or circuits that will be replicated many times, just a slight cost increase for a chip can quickly multiply. For this project, I decided on a PCB because really wiring it manually, even with just 13 chips, would have taken forever. On EasyADA, I can just name everything unique nets, and it will wire itself using an auto router. That reduced the time of wiring from hours to minutes. This was the final PCB here, which was honestly mostly made with looks in mind instead of the optimal wiring position, but I still like how it turned out. As you can see on the PCB, there's just a big hole in the middle. This is for the gray code dial that we were given. We need to give it back at the end, so in order to still include it in the project, I put it on a couple of female headers, but this also increases its height and makes it pretty high up. So to keep this supported, the case pokes through the PCB by this column and supports the dial. The second switch here, the second slide switch here, actually switches the inputs from the dial to the 4 dip switches and back. So even when I give the dial back, the circuit will still be operational. And you can see here's the actual case. You can see that this big column is what supports the dial. Inside it also holds a 9-volt battery in its base, and PCBs screws go through the PCB and into these 4 columns on the case, and that's how the PCB is actually secured to the case. That was my project 3.7 gray code. Thanks for watching.